Hey y'all, it's your math teacher, Mr. Boyden, back at it again today. And the reason I'm back at it again is because today we're starting a new unit. We're going to get into the IB unit regarding probability and statistics. So let's go. We're going to start out by talking about some basic vocab today. This may be new, but we have something called the sample space, which is all the outcomes that are possible for some event. So for example, if I flip a coin, what are all the possible outcomes? Well, either we could get heads or tails. So the sample space is heads and tails. Or if I throw a six-sided die or six-sided number cube, what are all the possible outcomes of sample space? Now, when I did this in class, a lot of students would yell out 6 as their answer to this. But guys, the answer to that is not 6. What that's saying, if you say 6, is that 6 is the only thing that can happen when you throw a die. Well, there are 6 things that can happen, and those things are 1, 2, 3, 4, 5, and 6. Okay, so be really careful about that. So that's for some event. What is an event? An event is just something that happens that has some probability. So we already talked about the sample space for flipping a coin. The things that could happen, it could be heads or it could be tails. That's a sample space. So let's talk about the very basics of probability. In general, the way we find a basic probability is we take the number of equally likely ways that something can happen, or the desired way it could happen, and we divide that by all of the different equally likely things that can happen. Now that sounds kind of fancy. I bet you already know how to do this though. So for example, what is the probability of getting heads when a fair coin is flipped? It goes like this. How many different ways could we possibly get heads? Well, there's only one head on a coin, so that would be 1. And how many things could happen when you flip a coin? Well, that's a sample space. That's 2 things. So 1 out of 2 is that probability. Let's go back to the example with dice for a second. Like, what's the probability that I get a 5 when I roll a die? So it's like this. How many 5s are there on a die? 1. How many different faces are there on a die? Well, in this case, 6. So that's 1 out of 6. And that's a little different than if we had, like, the probability of getting an even number when we roll a die. Because then we'd say, well, there's more than one way to get an even number. There's 2, 4, and 6. That's 3 different ways out of 6 different numbers on a die, so the probability of getting an even number simplifies to 1 out of 2. Okay? Now, let's ask a little bit more interesting questions. So what about if we flipped a coin twice? What would be the probability of getting heads both times? There are 2 approaches to this question. I'm going to show both of them. First, we're going to do the sample space way of thinking about it. So we're going to say, if we flip a coin twice, what are all the different things that could happen? Well, one thing that could happen is you could get heads both times. Another thing that could happen is you could get tails both times. You could get heads and then tails, or you could get tails and then heads. That's the 4 things that can happen. So of those 4 things, how many of them are the desired outcome? The desired outcome being getting heads both times. Well, that's just this one. There's only one way to get heads both times out of the 4 different things that could happen, and they're all equally likely. So the probability of flipping a coin twice and getting heads both times is 1 in 4. There's another way of doing this though. If you flip a coin twice, we could think about it as 2 independent events. So the first event is flipping the coin once. And what would be the probability of getting heads once? Well, that'd be 1 out of 2 because there's 2 faces to a coin. And then you flip it the second time, so we'll call this the first flip and the second flip. On the second flip, what's the probability? Well, it's the same. It's no more or less likely on the second flip to get heads. So 1/2 times 1/2, that's also 1/4. So the answer to this question is 1/4, but we've looked at 2 different ways of solving it. Sometimes we'll get more interesting questions where we have something like 2 dice, because a coin twice, it's still pretty simple probabilities. We're getting a little bit more interesting with rolling 2 dice at the same time and getting a sum of 8. And it's a little bit harder to think about because how many different ways can you get a sum of 8 when you roll 2 dice? So yeah, you get like 2 and 6, and you could get 4 and 4, and 3 and 5. So maybe there's 3 ways. Let's see. Anytime you get a 2 dice problem, well, I shouldn't say anytime, but many times when you get a 2 dice problem, making a rectangular array like this will be useful. They said sum, so I'm going to do addition, and this is going to be my first die, and I could get a 1, 2, 3, 4, 5, or 6 on the first one, and on my second one I could get a 1, a 2, a 3, a 4, a 5, or a 6 on that one as well. And now I'm going to find all the sums. So this first spot in the array, that would be like getting a 1 on both die. 1 plus 1 is 2. Right here, this is like getting a 2 on one and a 1 on the other. So that would be 3. A 3 and a 1, add those together and get 4. A 4 and a 1, add those and get 5. A 5 and a 1, add those together and get 6. A 6 and a 1, add those together and get 7. What about the next one? That'd be a 2 and a 1, that adds up to 3. Now notice, This one right here was also from a 2 and a 1, but it's a different event because in this case right here, the first, or the die on this side was a 1, and now for this 3, this die is a 2, so they're actually distinct. So now I'm just going to take a minute and fill in this table. You may have to pause the video to make your notes nice because I'm going to go pretty quickly here. Now that our table is complete, all we do is we're going to look at which of these outcomes end up with a sum of 8. So I've got an 8 here, 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 and here. Okay, so there's 1, 2, 3, 4, 5 ways to do that. So the number of ways to get the desired outcome is 5 different ways out of a total of how many different things could happen. Well, since this is a 6 by 6 rectangular array, 6 times 6 is 36, so the probability of getting 8 as a sum is 5 out of 36. Now, what if we said or asked if the probability that the sum is less than 8? How would that change it? So all we would do is we would identify the numbers in the table that are less than 8. So that would be all of these, and 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 that one. So I'm going to add those up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we'd say then that is 21 out of the 36 numbers in an array. Now, there's nothing magical about this word sum. Okay, if that word was a product and they were multiplied, that'd be fine. In fact, one student said yesterday, that's just a times table. Yeah, it is. It's a times table that goes only up to 6. So you could still make that and interpret it. But the reason this is important is many students cannot recognize quickly that there are 5 different ways to get an 8, or that there are 21 different ways to get a sum that's less than 8. So when you have the array, it becomes a simple counting exercise, and that will be a lot easier. Now, one thing you may have noticed about the probabilities in here so far is that all of them have been fractions of the value of less than 1. So that leads us to this question. How do we express 100% likelihood as a probability? Well, let's remember what percent means. 100% means 100, well, it's 100, but percent means out of 100. 100 out of 100 is 1. So the way we would express something that's 100% likely is with a probability of 1. In fact, all probability ranges from 0 to 1. There's no such thing as a negative probability. And your probability can't be more than 1. You can't have something that's more certain than a guarantee, and 1 is an absolute guarantee that something will happen. So let's talk about the spectrum of probabilities then. And what I mean is we're going to label vocab of the probabilities that go from 0 to 1. If something has a probability of 0, we might say that that is impossible. What if something is guaranteed? So guaranteed would be one word, certain would be another word, it's certain to happen, although the fancier word for it is that it would be inevitable. And those are the ones that are clearly definable. Impossible is 0, inevitable is 1. The other terms I'm going to throw out here are not as obvious. So we have impossible. The natural other word we would need to include is possible. A lot of people say possible is somewhere up in here around 0.5. And technically, anything more than 0 fits in the realm of possible. However, let's consider the way that we would usually use the word possible in a sentence. We might say something like, well, I mean, it's possible that it could snow in June. It is possible. I mean, very, very, very unlikely. It's possible that you could win the lottery. Yeah, it is possible, but really unlikely. So the way we use this word socially, usually it's down in here somewhere. Like, it's probably not going to happen, but it is possible. If something is a little bit more likely than possible, like, yeah, it seems like reasonable, that's more like plausible. And the one that some people struggle with still is the word probable. Well, just remember, probable is like the same as probably. So if you say like, we're probably going to win the game tonight. How likely is that? Is that a 50-50? Nah, probably is not a 50-50. It's more likely than not. So probable is definitely somewhere over here. Now, this is not something that you'll necessarily ever be tested on. These words are good to know. The reason I bring them in here is, as an educated human being, these are terms you should know and know how to use. So I'm just giving them to you now so that you can use them in your own conversation. Now let's try to answer some questions that are a little bit more challenging. We'll start here by talking about Tommy. So imagine that Tommy is given a list of 20 questions, and it could be any class, doesn't matter. From that list, the teacher's going to make a test that has 10 questions. So Tommy already knows what all the test questions are going to be, or already has access to all of the possible test questions. He just doesn't know which 10 will be on the test. The teacher will pick 10. He knows how to do 17 out of the 20 questions. So what we have to figure out is what's the probability that he can get 100% on the test. And what I'd like you to do is I'd like you to try to make a guess before we do any work at all. Just logically in your mind, does it seem like he has a good shot at getting 100% on this test or not? He knows how to do 17 out of 20. Let's see what happens. Let's consider the series of events that would have to transpire in order for Tommy to get 100% on this test. First of all, he'd have to get the test and he'd have to look at question 1. And let's figure out how likely he is to get question 1. He knows how to do 17 out of the 20 questions, and they're going to be chosen randomly, so he has a 17 in 20 chance of getting question 1 right. What about question 2? Does he have the same probability? No, because we already found the probability that he knows how to do the first one. One of the questions that he knows how to do was already used, so he only knows how to do 16 of the remaining questions. And since it's not going to be the same question all the way through the test, each question will only be used once, there are not 20 questions to choose from anymore. There's only 19 questions the teacher can choose from. What about question 3? Now, Tommy already knows, he's already done 2 questions he knows how to. There's only 15 left out of the 17, so that's 15 out of 18. Do you see the pattern yet? It should be pretty simple at this point. I'm going to fill these in. So question 4, question 5, question 6, question 7, question 8, question 9, and question 10. And then let's fill in the probabilities, because I'm just going to use the pattern to finish this out. All right, and there's all the probabilities. Now, this is the same idea as when we had 2 coin flips back to back. We multiplied the 2 probabilities together because those were independent events. So these, well, technically are dependent because the probabilities are changing, but the math works the same way. So we need to multiply these all together. Now, this is kind of a throwback to the beginning of the year when we talked about factorials. Because look, if all these are multiplied, like you got a 17 on top and a 17 on bottom, and they cancel. And let's see what else will cancel. You have right here 16 all the way down to 8, and here you have 20 all the way down to 11. So which of these match up? Well, there's a 16 through 11 here and a 16 through 11 there. So this 16 through 11 cancels out this 16 through 11. So those are all gone. And let's rewrite what we have left. In the numerator, we have 10, 9, and 8. And those are not decimals. That's signifying multiplication. And 20, 19, and 18. Let's simplify this in the easiest way possible. 10 divided by 20 is the same as 1/2. 9 divided by 18 is the same as 1/2. I can't simplify 8 over 19, so I'm going to say 8 over 19. Those are still all multiplied together. So now let's say 1/2 times 1/2 is 1/4. And that's times 8 over 19. And that works out really well because we know how to divide 8 by 4. That's 2. So 2 over 19. So, how likely is Tommy to get 100% on this exam? Well, not very likely. I mean, 2 out of 19, that's not very good odds. So how can we apply this to ourselves? Guys, it's really, really hard to get 100% on a test, and this math, I hope, reveals a little bit of why. Because in order for you to not to get 100%, you only have to miss 1 question. And if there's 3 questions out of 20 that you don't know, there's a pretty good chance that you're going to miss at least 1 question on the test. Let's look at an example now with the Rhode Island Lottery. In the Rhode Island Lottery, players pick numbers from 1 to 35, and 5 of them. 5 different numbers are selected at random by the Lottery Commission, and they are different numbers. And any person who has the matching numbers in the right order, they have to be in the right order, they're a winner. Now, Rosie wants to win, so she's going to buy 40 tickets. I mean, she's serious. She's going all in on this. And she's going to put different numbers on each one of them to up her odds of winning. We want to know what is the probability of her being able to win in this situation. I'd encourage you to pause the video and try this one. I think that you probably could get a lot of the progress on it. If you need a little boost, we would think about what series of events has to happen. Same with Tommy, like what series of events has to happen for her to be a winner. So here's what it would be. The first thing that has to happen for Rosie to win is she has to get the first number right. There are 35 numbers. She only has 1 in that first slot, so she has a 1 in 35 chance of getting that first number. Now, since they're going to pick 5 different numbers, the number that ended up being the first has already been used. So for her to get the second number right, her probability is a little bit higher, 1 in 34, because one of them has already been used. What about the third? Well, now two of the numbers have been used, so it's 1 out of 33. And then the pattern continues, 1 out of 32 and 1 out of 31. And we're going to multiply all of those together. Now, what about this? She bought 40 tickets. When you buy 40 different tickets, your odds increase 40 times over. And a lot of people fall into this trap, y'all, because they say, oh, I want to have 40 times more chances to win. I'll be 40 times more likely to win. Well, the problem is, this set of fractions multiplied together is an eensy-weensy, teeny tiny number. So 40 times an eensy-teensy, teeny-whiny number is still a really small number. Okay, so I'm going to type that in my calculator here. So 40 divided by, you may have to be careful to make sure you put these all in parentheses, or otherwise your calculator may misinterpret it. And oh my goodness, what a small number this is. 0.0000001. Okay. Let's interpret that. Let's do that as a percentage, because maybe that'll be easier to think about. That would be a decimal slide of 2, so that would be 0.0001%. Uh-oh. That's not very likely. 1/10,000th of a percent? Uh-oh. Rosie, you might want to find a better place to spend your money, because you're probably not going to win the lottery. What about the complement of an event? Guys, you probably learned in geometry that the complement of an angle, or two complementary angles, would be like two angles that add up to 90. They complete a right angle, and the root word of that is complete. I don't mean to cross it out, I mean to underline it. Let's see if I can do a better job. Hey, there we go. Complete. The way we write it is right here. I know that sometimes in math that apostrophe is pronounced as prime. However, in probability it's pronounced as complement, so this is a complement. And I want you to think of it as the probability of something not happening. Now, the way it connects to this is that the probability of any event and its complement will always add up to 1, the sum total of everything. Because what that's saying is like the probability of A happening or not happening. Let's do an example. The probability of us winning our tennis match plus the probability of us not winning our tennis match is going to equal 1. Because that's encompassing the whole sample space. That's all the things that could happen. We could win or we could not win. That's it. So of course it has to add up to 1. So we have an example here. If FOSS, there are 618 students, 344 of them are upperclassmen. If a FOSS student selected at random, what's the probability that the student will be an underclassman? So here's why it's complementary thinking. Because we would first need to know how many underclassmen there are. And that's pretty easy. We know that there are 618 students, so if we subtract out the upperclassmen, then we will know the number of underclassmen. And that is 274. So if we want the probability of that, I'm going to put probability of under, we would think how many different ways are there to pick an underclassman? Well, there's 274 ways because there's 274 of them out of the grand total of how many? 618. And I'm not going to spend the time in this video to simplify that. You could if you wanted, but that's the probability. I will turn it into a decimal. So, oops, if I typed it in wrong. So 274 divided by 618, and that is 0.443 is how we would round that. So that is the probability, a little bit less than 50% likelihood, 44% likelihood of selecting a student that is an underclassman. So with that, let's do one of my favorite exercises in really all of math. It's one of my favorite things that I teach. That's the Monty Hall problem. The Monty Hall problem goes like this. You're on a game show, and they call you down, and there are 3 doors. All right, 1, 2, 3. And behind one of the 3 doors is a brand new car. And so you want to select that one, but because behind the other 2 doors are things like, oh, I don't know, maybe a student loan and an assignment to do some hard labor or something like that. So you really would like to select the car. And so you pick a number, and let's pick a number. Let's pick, I don't know, 3. Why not? Let's say you select 3. So here's what's going to happen. The game show host is going to say, wow, that's a good choice. Well, let's see here. Let's open up door number 1, and behind door number 1 is a student loan. Congratulations, $100,000 in debt. And you say, whew, that was a close one. I'm really glad I didn't pick door number 1 because I would have had a student loan, and that makes me feel better about 3 because maybe there's a car behind door number 3. But then the game show host, who is Monty Hall, he says to you, all right, you've picked door number 3. How confident are you in your choice? Because I have a one-time offer for you, and you have to decide right now. If you would like, you could change to door number 2. Or if you want, you can stay with door number 3. That's totally fine. So here's the Monty Hall problem. What should you do? Should you switch or should you stay? What is in your best interest? Are you more likely to win the car if you stay with door number 3? Or are you more likely to get the car if you switch to door number 2? So I'd like you to pause the video and spend a little bit of time thinking about that. You actually can calculate the exact probability of winning based on either strategy. And the strategy is, should you switch or should you stay? So I'd like you to find the actual probabilities, pause the video and try it and figure out what you'd like to do, and then I'll explain how it works. All right, so here's the solution. When we picked door number 3, there were 3 doors, so our probability of winning was 1 in 3. Not great. Which means that our probability of losing was 2 out of 3. Now, when they opened up door number 1, a lot of people assume this becomes a 50-50 proposition because there's only 2 doors. But it's not. And it's not because the car doesn't move. It's still going to be in the same spot. So while the probability of winning was 1/3, and the probability of losing was 2/3, now that this door is open, that 2/3 now is associated with door 2, so you should switch. Now, the math of that may not feel very intuitive, so let me describe it in a different way. Let's consider if you're doing the stay strategy. What does it take in order for you to win? How do you win? What does your first guess have to be? If you stay, the only way to win is if your first guess is right. And the probability that your first guess is right is 1/3. But what if you do a switching strategy? In fact, let's think about it the exact opposite way. How would you lose in a switching strategy? If you wanted to lose in a switching strategy, the only way to do it is if your first guess was right. Which means you automatically win. So the way to win is if your first guess is wrong. Because if your first guess is wrong, let's say 3 was wrong, then Monty Hall is going to reveal another wrong answer to us, which means that the only other answer up here is the right answer. So you automatically win in a switching strategy when your first guess is wrong. And the probability of your first guess being wrong, well, we had a student loan behind one door, and we had hard labor behind another, so that's 2 out of 3. That's another reason why you must switch. So what have we learned today? The lottery is not a winning proposition. And if you ever get on a game show like this, you must switch because it actually doubles your chances of winning, believe it or not. Let's talk about Venn diagrams. Usually in class, when I ask students what Venn diagrams are, they draw this right away. And they say, well, you have, it's like for compare and contrast. Like the area in the middle is things that 2 topics have in common, and the things in the bubbles are things they don't. That is a useful understanding of Venn diagrams. However, it is possible to have a 1-bubbled Venn diagram. So maybe it would be like this. Like I might have Mr. Boyden students. And they would go on the inside, and I have like 135 students. And then on the outside would be all the students which are not in my class, or I should say who are not in my class. And that is maybe, I don't know, 550 or something like that. Okay, and so here I have this box around it. Now, if you're doing like an English rough draft or something, this is going to work great, guys. Okay, I'm not trying to change your understanding of Venn diagrams generally. However, to do them in a mathematical sense, we usually need to put this box around to represent the universal set. Also, it is possible to have more bubbles. I mean, there's no reason why you couldn't have 3 or even 4 bubbles in your Venn diagram, or even more. I mean, really, you can have any positive number of circles in your Venn diagram. The one that's going to most often be useful in IB math or in math in general in pre-calculus is the 2-bubble Venn diagram with the box around the outside. So let's do an example of that so you can see how it works. In a group of 50 students, we have 37 that take Spanish, 12 who take Korean, so those are going to be our bubbles, and 8 who don't take a language course. We are asked to provide the number of students who take both Korean and Spanish. So that's going to be that intersection, the overlap in the middle. So bubble, bubble. Let's do Spanish and Korean. So here's what a lot of students normally do. And actually, I'm going to do this. There's 50 total, so I'm going to make a note on the outside of here that the stuff inside the box should add up to 50 because we're accounting for 50 students. So there are 37 who take Spanish, and there are 12 who take Korean, and there are 8 who are not taking a language at all. Now, guys, astute students will point out that these three numbers don't add up to 50, and so that seems like a problem. These three numbers actually add up to 57. So you go, wait a minute, what the heck? We haven't even written a number here in the middle yet, and that's the answer to the question. So that's what we have to know. So how can that be? How can it be that we already have too many students, but we haven't done the ones in the middle? Well, guys, here's what's happening. Some of the students here, to get this larger number, are being double counted. Like, they're taking Korean and they're taking Spanish, but they're being counted once in each bubble, which means they're being double counted. Well, how many students are being double counted? Well, how much too big is this number? This number is too big by 7. That's 57, and we thought it should be 50, which means that there are 7 students who are being double counted. Now, you have to be careful because right now, according to this diagram, how many students take Korean? It's actually 19, because you've got 12 here and 7 there. Both of those are in the Korean bubble, but there aren't 19, there's 12. So what we have to do is come in here and we have to change that. And I'm going to change it down to 5, and now 7 plus 5 is going to be 12. Same thing over here. So if 7 are there, we just need to take 7 off of here and make that 30. So now how many students, according to our diagram, take Spanish? We have 30 and we have 7. That's 37. How many students take Korean? 5 and 7. That's 12. 8 take none. So now this is an accurate diagram, and we can answer the question. How many students take both Korean and Spanish? Boom, there it is, 7. All it is. And if you double check, adding these 4 numbers together adds up to 50 students. So now we're guaranteeing that every student has been accounted for exactly once, and we know how many students take both. Let's do another one to get more practice. I'd like you to pause the video and try this one on your own. All right, we have ghosts, we have Loch Ness monsters. Again, we have 50 people. So there are 22 who believe in ghosts, and there are 14 who believe in Loch Ness monsters, and there are 6 who believe in both. And so we have to figure out how many believe in neither. Now, I hope you can already see there's a problem, because according to the way I drew this, how many people believe in the Loch Ness monster? 6 plus 14 is 20. That's not right. It needs to be 14. So what I need to do is I need to subtract 6 off of this and make it 8, because now we have 14 people in the Loch Ness monster bubble, and we still have 6 that are doing both. Same thing over here. This adds to 28, so I need to subtract 6 off of right here, and I get 16. So how do I figure out how many people believe in neither? Well, what I have to do is I have to figure out how many people do we have in the diagram right now. So we've got 16, 6, and 8. I'm going to add those together. 16 plus 6 plus 8. And it looks like we have 30 people accounted for, which means that how many more do we need to get 50? 20 more. So there are 20 people in this group that believe in neither. Now let's change gears for a moment and talk about conditional probability. Go ahead and write down the symbols here. Pause the video if you need to, because I'm going to start explaining it. This symbol right here is an intersection. Okay, and it translates as the word and. And here's the reason why. Like on our Venn diagram, the intersection is this part in the middle. It's where the 2 lines intersect, or where, not the lines, excuse me, where the 2 circles intersect, where they're overlapping. It's the part of the circle, or the place where I can put my pen. Like if I put my pen right here, that dot is both in circle A and in circle B. Okay, it's in both. Over here, this is probability of A, so being in A. This is probability of event B, given that we know A has happened, or given that A is happening. So let's do an example here. And I'm going to show you how you don't actually need the formula. It's going to be unusual that you would use the formula, actually. I'm going to show you a way to do it more intuitively that should be quicker and easier for you. At FOSS, the junior class has 163 students. 163. 46 play a sport. 44 take psychology, 85 do neither sports, nor psychology. So let's add these three numbers up. So 46 plus 44 plus 85, we are at 175. Notice that is 12 too large, which means 12 students have been counted twice. So when I go to fill in the sports bubble, I'm not going to put 46. I'm going to put 12 less than 46. I'm going to put 34. And when I go to put in the psychology bubble, I already have 12 accounted for, so I need to write 12 less than 44. That's 32. So how many do both? 12. That's how many. So that's that intersection right there. Oh, one thing I forgot to mention. One way to keep this straight and remember it, that symbol, you see how if you just put a little cross across it like that, it looks like the letter A, goes as and. That's how you can remember conceptually what it is. So let's get to the conditional probability now. What is the probability that a student takes psychology given that we know they play a sport? So when it says given that we know they play a sport, what that's telling us to do is focus only on students who play sports, only on the bubble of sports. And they're asking about, within that bubble, how many of those students take psychology? So let's answer that question. How many of these students take psychology? Well, just that 12 out of how many play sports? Out of the 46 that play sports. And then we get to simplify that. Those are both divisible by 2, so that would be 6 over 23. That is the probability that they take psychology given that they play a sport. Let's do it in the reverse order now. If you want to pause and try it on your own, that's fine. What is the probability that a randomly selected junior from psychology, so this is the same thing but different wording. So a junior from psychology, that's the condition. So they're from psychology class. What is the probability that that person participates in sports? So now we're talking about psych class, so we're only looking at the psych bubble. Okay, so look inside the psych bubble. How many are in there? 44. So it's out of 44. Of those 44, how many participate in sports? 12. So 12 out of 44, both of those are divisible by 4, so that's 3 out of 11 is the probability that a randomly selected junior from psych participates in sports. And our final thing we're going to talk about today is tree diagrams. So we're going to do the tree diagram, and then we're going to answer a couple questions with it and see how this would have been really hard to deal with if we didn't have a tree diagram. The way I'm going to teach this is just with one really big example. Now, it's unusual that you'd have an example this big on a test, but I think this will illustrate an important concept really well. Okay, and so the topic on this comes from one of my students' papers from the class of 2014, and it's a little bit morbid, but it is a really good example of the statistics, and so that's why I'm including it in this video. Okay, here it is. Make a tree diagram for the following. Half of all men will get cancer in their life. So who are we talking about? We're talking about men. And some of them will get cancer, and some of them will not. So half will get cancer, which means that half will not. So check, we got the first part. Of those that do get cancer, 3 out of 5 will undergo surgery. So that's 3 out of 5 will undergo surgery, which means that 2 out of 5 will have no surgery. Check. 1 out of every 4th man diagnosed with cancer will die regardless of whether they have surgery. So surgery or not, they might live or they might die. If they have surgery again, they might live and they might die. And the probability of that is 1 and 4 will not survive. Okay, so 1 and 4 will not survive, which means 3 out of 4 will. So 3 out of 4 will survive, 1 out of 4 will not. And that's because they said regardless of whether they have surgery. Okay, we got that down. 3 out of 5 men who survive the first operation, so cancer, surgery, survive, will go through a second operation. So either they will go through a surgery or they will not have a surgery. And we are told of those that will have surgery, 3 out of 5 will have a second surgery, which means that 2 out of 5 will not have a second surgery. And of those who go through a second surgery, 3 out of 4 will go into complete remission. So guys, I'm going to be consistent here. So remission, I'm going to call that they will continue to live, and then they will not survive is the other option. Okay, so 3 out of 4 will experience complete remission, and that means 1 out of 4 will not. Okay, so that's a completed tree diagram. It has a lot of steps, and it's not symmetrical. Notice, no cancer, it just stops. They're not going to have cancer surgeries. They're not going to have the events of life or death. If they have no cancer, they will not die from cancer. There'll be something else that gets them, but it won't be cancer. Okay, and so this is a lot of information over here. If we take this information and have to do questions on it on our own, it's really hard to weed through all that information. But if we are able to get a diagram like this, we're able to answer questions. So let's try to answer those questions now. Questions. What percentage of all men will die after having 2 operations to treat a cancer? So some people try to oversimplify this and they say, all right, cancer, 2 operations, and then die. They go, oh, it's 1/4 of all men. But no, it's not that simple, because you have to think, in order for a man to fall into this category, what series of events have to happen? And this is the 3rd time I've said that in this video. It's not that just one thing has happened. This is a whole bunch of events. So in order for this to happen, the first thing that would have to happen is you would have to be diagnosed with cancer, and that's only a 50-50. Then you'd have to need surgery as a treatment for your cancer. Then you would have to survive that one, so 3 out of 4 for that. From here, you would then have to have a second surgery. That's only a 3 in 5 probability. And from that point, you would have to not have it be successful. You would have to pass away. So it's not as simple as a single probability. What we end up doing is we figure out where on the tree is that, and then we multiply all of the probabilities that represent the sequence of events that lead to that location. So I'm going to take a minute and type that in. So it looks like the numerator is 3 times 3 times 3, which is 27. We're going to divide that by the product of the numbers in the denominator, so divided by the product 2 times 5 times 4 times 5 times 4. And I get 0.03375. So that would be 3.375%. And I'm going to label that up here, that this outcome for a man happens 3.375% of the time. All right, what about the next one? What percentage of men are going to die from an inoperable cancer? So let's trace the series of events. So starting out with a man, so it's sort of conditional probability, because the condition is you have to be a man to be in this question. So you would first have to be diagnosed, that's a 1 in 2. It would have to then be inoperable, so no surgery, so that would be a 2 out of 5. And they're talking about a not successful surgery, so that would be 1 in 4. So let's multiply all those together. That is 1 over 20, which is 5%. All right, so I'll label that up here as well. And then what at the end? What percentage of men will die from cancer? So what we have to do is we have to come back up here and we have to identify all of the ways that can happen. It could happen here. It could happen here. It could happen here. We already know 2 of those probabilities, so we just need to find this one then. So in order to find this one, what we do is we multiply along the branches of the tree that lead there. So 1/2, 3/5, and 1/4. So let's multiply those together. So 1/2 times 3/5 times 1/4, and that is 7.5%. So in order to determine the total probability or the total percentage that will die from cancer, we have to add all these together. So 3.375 plus 7.5 plus 5. And what we get is that about 15.9% of all men will die from cancer. That will be their cause of death. Okay, and guys, I know that's kind of a morbid example to end the video, but there's always going to be a leading cause of death, and there's something that's going to get all of us. That's part of being human. This is the math of it, and what I'm trying to show you here is that basically it can be very complicated to think about all of these probabilities at once. However, when you organize them in a tree diagram, they become really, really simple to calculate. Okay? Hope this video was helpful. Hope you enjoyed it, and we'll see y'all next time.